OK なんかあっちからも聞こえるな。こっちミュートにしやない。Thank you very much for coming back to this unofficial part of the lecture series. I'm not sure if I should use English or Japanese and English, OK? いやいや、多分日本語喋らない方もいる。Okay, so this is the continuation of the lectures from last semester about algebraic topology aimed for theoretical physicists. So the main reason why I got interested was that algebraic topology allowed me to systematically understand anomalies in terms of something called invertible phases, a close cousin of symmetry protected topological phases in one higher dimension. And so I wanted to talk about it because there's no good place for theoretical physicists to learn these stuffs. So I wanted to write a lectures notes. And to prepare lecture notes, it's best to actually give lectures and write them down. That's why I started last semester, but I couldn't actually come to talk about symmetry, protected topological phases, etc. So I really want to continue it. So I'm very glad that Takasan-san reserved this room for the continuation and any of you to come back so that I can continue this discussion of the applications of somewhat more modern algebraic topology to theoretical physics. And during the last semester, I typically introduced mathematical concepts without talking about physics, and then I discussed various physics applications. But in this second part, I think I will get closer to a more standard style in theoretical physics of first giving you motivations why you would need such a concept, and then introduce math definitions, etc. So the topics I want to cover in the second half are, roughly speaking, as follows. So first, I'd like to discuss classifying space for finite group. So this is an interesting example where you can do many actual computations. And this has applications to both Condomat and HepTH. So this is a nice playground to learn actual computations in algebraic topology. So this is a good place to learn. So this is kind of a continuation of the first semester. And then I will switch gears a bit and would like to talk about topological insulators and superconductors from a rather abstract point of view. And I'd like to discuss its relation to K-theory and KO theory. So this will lead to the famous periodic table of these topological insulators and superconductors. So that's the second topic. And we will learn that these are these give classifications for the free non-interacting fermionic phase. And I'd like to end this series of discussions by talking about classification of interacting fermionic topological phases. I mean, SP, symmetry protected topological phases. And this will require us to learn something called cobordism groups. And it's Anderson dual. So once you learn these stuffs up to this point, you are perfectly ready to go to learn whatever theoretical physics papers using these modern algebraic topology stuff, both in Condomat and HepTH, and you will not have too many problems deciphering what is going on. So once you come to this point, all of the understanding of the basic concepts are done. But then, unfortunately, in algebraic topology, understanding the concept and being able to compute are quite different things. So as the fourth step, if I still have some time, I might present many example computations. With tools, necessary tools. So that's the idea of the second part of this lecture series. I don't know how long it will take. So I mean, it's perfectly okay for you not to come back. I think I would continue until nobody remains. Yeah, but I mean, once we get to the point that there are zero audience, I'm not sure if I continue recording it, but I intend to finish writing up this lecture notes so that I mean, you can just have a look at it and learn the necessary techniques. So that's my intention. So I really would like to thank you for coming back and giving me this opportunity to explain what is going on. Right. So today's topic is this classifying space for finite group. So that's the first topic we would like to discuss. So what was the classifying space? So let G be a group. And during the last semester, we talked a lot about something called principal G bundles over a manifolds M. So this is abstractly defined by covering M by patches, and on each patch you have G, which is just a product, but over the intersection of the patches, over the intersection of the patches, so let me write it bigger. So you have copies of G here, copies of G there. But when you go from one patch to the other, there is an element Gij, which is a function from the overlap to G, such that the coordinate here and coordinate there are mapped using the product by this group element. So this is like a twisted product. And the classifying space was such that principal G bundles over M up to bundle equivalence is in one-to-one correspondence with a map from M to BG up to homotopy. So at the end of around the end of the last semester, I just stated two facts about BG. So first, the important fact was that BG exists for any G. And characterizing feature of BG is that there's a bundle, principal G bundle over BG itself, which is usually called EG over BG, such that this is contractible. So from the homotopy theory point of view, it doesn't have any feature. So it's like a point. And G action is free. And by free, you mean that there's no fixed point. So that's the definition. And during the last semester, we actually talked about only a few such BG. So, I mean, we said, BZ was simply S1. And the BU1 was CP infinity. And the BZ2 was RP infinity. And I forgot if I actually discussed this, but during the last series of lectures, I always treated RP, RC, and quaternions in a parallel fashion. So exactly by the same argument, you can, if you can show these two, you can also show this. And we only discussed these these four. I cannot even count. So, this is not very convincing, right? For each of these examples, we used various extremely specific features of these groups to construct the classifying space. So it's doubtful at this point if this is really true, or you can do any actual computation using it. And for HEP-TH purpose, group UN is very important. So BUN would also be interesting. And this has a very nice explicit geometric realization, but I will postpone the discussion in view of time. But instead, I'd like to start the second part by talking about BG for finite group G. Because, well, this also gives us a nice class of examples, and this has both Condomat, lots of Condomat and HepPH applications. So I'd like to discuss this. I'm going to actually just construct EG. So it was, the following construction was first found by Milner, if I remember correctly. I'm just going to directly construct this EG as a space. So let's construct EG. As a simplicial complex. I wrote as such in the lecture notes I prepared. But if you carefully look at the actual construction, I haven't corrected it. But while I was walking toward this building this morning, I realized that it's not really a simplicity complex, but it's a CW complex. Yeah. But I will actually build it. So let me pretend that it's a simplicial complex. So I'm going to build it one by one, step by step. So as zero simplices, we take for each element G in G, I introduced a point G labeled by G. Okay. And then as one simplices, I just pick two elements from capital G, and I introduce an edge connecting G1 and G2. Okay. So when G is, say, Z3, I mean, there are 3 points, and then I introduce edges for all of them, but I also introduce loops because I'm allowing all possible elements from G. So that's what you do. And then for two simplices, I just pick 3 elements from G, and I introduce triangles connecting all G1, G2, G3. For 3 simplices, I just take 4 elements from here, from the group, and you introduce tetrahedron with vertices given by G1, G2, G3, G4. and so on and so on. So it's a very obvious construction. Once you realize it, you just choose all possible elements and in all possible permutations and introduce simplices corresponding to each of them. And so we are going to fill this in, 0, 1, 2, right? But this, it also has things in the opposite order, 0 to 1, or 2 to 1, or 0, 0, 1. I mean, it's very difficult to visualize how all of these things are put into a single object. It's not definitely manifold, but it is almost a simplicial complex. The definition of the simplicial complex is the collection of simplices which intersect nicely. So if you open up the math textbooks, a simplicial complex requires that you don't have a self loop, for example. And so here we have lots of overlaps, I mean, and redundancies. So this is not really a simplicial complex, but it's still a CW complex. It's a very degenerate space. So I think this is a kind of an example of a space which is better understood by your logical mind rather than trying to imagine or visualize in your head what is going on. But this is the definition of our explicit construction of EG. So it's just that you have K simplex for each G1, G2, GK plus 1, such that it has faces corresponding to each of the subsets, right? So and it's pasted in an obvious way, at least locally. So that gives you an explicit pasting operation. So it is really just a CW complex. And the G action, so we need to check that it's actually EG. So you need to check that it's contractible and the G action is free. G action is just given by multiplying, sending this to another simplex labeled this way, just by multiplying every vertex by G and mapping this K simplex to the other K simplex in a linear fashion. And clearly, the first vertex is always moved by a non-trivial element G. So the only fixed point is by the identity element. So this action is clearly free. It is also contractible because of the following. So this intermediate step in the case of Z3 is in a typical situation. So you want to actually give a way to contract everything into the origin, right? It's very easy to do so. So we have but suppose you have a point on this one simplex. There's a two simplex containing it with one additional vertex 0. So you just connect it by linear line, straight line, and you just contract it, right? It's very easy. So this construction can be generalized in an obvious way to higher dimensions. So because this space EG is constructed step by step, every point is contained in a K-simplex. Whatever point is an interior or on the boundary of a K-simplex, which is labeled by G1, G2, to GK plus 1, right? But by construction, this is always a face of K plus 1 simplex with one additional point. Therefore, any point here can be contracted along a straight line inside this K plus 1 simplex. So in this construction, it's very important that for any K simplex, we had a K plus 1 simplex with one higher dimension. So in order to guarantee the contractibility for arbitrary finite group G, it is necessary to have simplices with arbitrarily high dimensions. So even for Z2, in order to guarantee the contractibility, we needed to introduce a million dimension simplex, etc., etc. But just because you have a simplex which is one dimensional higher, you can always contract. So this is contractible. So this is really BG, I mean EG. Yes.
Here the orientation for
Yes. Yes.
there also orientation for quantity.
Yes. So in this construction, we are adding actually edges in both directions. Yeah. Well, yes, go ahead.
I still don't well understand the definition of free. So free in the no fixed point.
That's no fixed point other than by the identity element. Yes, I mean for any group action, if you take the identity, every point is a fixed point. So
if the usually if they take the constitutional group, it is obvious.
right.
Free. And also another thing, EG have indices of K, right? So like,
right.
If we have some finite group G, then the EG have can be need to have a large K or some set of the simplistic or I don't know how to say. K simplex itself is EG or some or combination of one simplex, two simplex, three simplex.
EG is obtained by pasting all of the zero simplices, one simplices, and 10 to the 10 simplices, and to infinite dimension. So you paste all of these simplices into a big complicated space. That's EG. But the important simplification in this case is that at each finite dimensions, there are only finite number of simplices. So once you set up the maximal dimension you want to consider, there are just finite number of them. But in order to guarantee contractibility, the dimensions, right. Go ahead.
What's an element of EG? Is not a here. Okay, so when you say a simplex, you can label it by G1 to G.
That's right.
Just that, you also need the the geometrical property.
So for each simplex is named by their vertices. So one simplex labeled by G1, G2 consists of the edge abstract edge parameterized by 0 to 1.
So like, it's also labeled as distance between G1 and G2.
That's right, that's right. Yeah. So two simplices. So there are G2 cube triangles. And each triangle consists of, well, just a triangle parameterized by two real parameters.
With like a bunch of different.
Yeah, for each different choice of discrete labels, G1, G2, G3, you have two parameters. So this is the triangle, and you just paste them.
So you're saying when it's contractible, you say that you have a topology, which is like.
Yeah, topology coming from this, metrical structure. But it's pasted in a very weird way. So it's definitely not a manifold in this construction. So for three simplices, there are G2 fourths of them. And then you introduce three real parameters, say STU. So what I'm saying is that you prepare such simplices for each choice of discrete labels, fill them into an actual simplices, and then paste them according to the labels attached to the spaces. Yeah. So we constructed EG. So what's BG? So BG is EG divided by the group action G. So, but it's kind of easy to get a cell structure of this because the identification is that each K simplex is mapped by G by just a simple multiplication. So for each, every G orbit of K simplices contains a simplex of a form E G1, G2, GK plus 1. Sorry, GK. Right? So we always, G action always multiply every element by G. So using this, you can always fix the first label to the identity. And that uniquely fixes the representative because G action from the left always moves it. It's customary to label this cell. This cell is usually parameterized as E G1, G1, G2, G1, G2, G3, G1, G2, GK. It's just a choice of redefinition of labels from G2 to GK. And in order to shorten the notation a bit, let's define it. Introduce a new notation we use vertical line to separate GK. So this is the K simplex of BG, not EG. So let's study the following question. Given a K simplex, G1 bar, G2 bar, GK, what are the faces? So that's the question we would like to ask. Again, in my opinion, it doesn't really help to try to visualize, but so this corresponds to a cell of this form, G1, G1, G2, and G1, G2, G3, say, then its boundary consists of E, G1, G1, G2, and E, G1, G2, sorry, G2, it's E, G1, G2, G1, G2, G3, and what are the four faces? I mean, it's G1, G2, G1, G2, G3, and I think I have another face. E, G1, G1, G2, G3, right? There are four faces. And you need to be careful about the orientations, which I wasn't very careful at all. There are plus minus signs. And we need to come back to this bar notation. So in the bar notation, they become just G1, G2, say, and this will be G1, G2, G3. And this would be just G2, because we remove this G1 by the G action, G2 and G3. And finally, this one becomes G1, G2, G3. Right, so there are these four faces. And I can never remember the signs. But so the correct sign is G1, G2, G3 plus G1, G2, G3 minus G1, G2, apparently. So this type of construction can be generalized to higher dimensions. So it shows how this complicated space BG was actually built. So it's quite explicit. So now we have BG. And the BG is supposed to classify all G bundles, right? So the definition of classifying space of G is such that principal G bundles over M up to bundle equivalence is in one-to-one correspondence with homotopy classes of maps from M to BG, right? So you might want to know how this relation is realized in this strange construction of BG. But if you really carefully expand and unwind the definitions, it's actually quite tautological. So let me construct map from this to that, right? So M is covered by patches UI, UJ, UK, dot, dot, dot. And using a fine enough cover by patches, you can construct dual triangulations of the manifold by choosing a point from each patch and having a edge connecting each of the chosen points from each patch if they intersect, and having a triangle if three patches intersect, etc., etc. So let's suppose that your manifold M is covered by triangulations, and the patch is centered around each of the points. And recall the definition of the principal G bundle. So what happened was that between two patches and the intersection, there is a map from the intersection to G, which was Gij, right? But here a big simplification comes in because we assumed G to be finite and discrete. And our requirement for a fine patch is that each of the intersections are contractible. So this is just a constant. This is constant map. So Gij, a patching function for the bundle G floating above here, is not really a function depending on the point of the overlap, as in the case of U1 or UN. Because this G was assumed to be finite, it's just a single element in G. So you can assign element Gij for this edge, element Gjk for this edge, and element Gjik for this edge, right? And then there's a tetrahedron and one additional vertex. You can consistently assign all of the group elements in this way. With this data, I mean, almost by definition, principal G bundle is the collection of such data. Now, given this, it's very easy to construct a map from this data to BG, because, I mean, all you have to do is to map, I forgot to say, but in BG, the only zero simplex is this, right? The notation is a bit degenerate. But in EG, zero cells, zero simplex are labeled by G. And by G action, this is fixed to be identity. And we decided that the first element is not listed, so it's just empty. But there's just one zero simplex. So we decide that every representative point from the patch is mapped to this single. So we send the chosen zero simplex here to the single zero simplex of the BG. And then we map this edge into the edge we denoted by Gij. And this is mapped to Gjk. And this is mapped to Gik, right? And then I'm running out of colors, but this triangle is mapped to that tooth. I mean, this is the part where I can no longer draw it in a nice way, but we just map this into the two simplex labeled by Gij slash Gjk, right? So the data assigned by the transition functions, which are not functions but actually constants, on the G bundle side is literally the assignment of how these simplices constructing the base manifold M into BG. So the fact that the G bundle on this side is constructed in a consistent way translates to the fact that this map pastes in a consistent way on this side. So once you unwind all of the definitions, it is almost literally true that G bundle data here is translated to the map to BG constructed in this explicit way. So that's how it is realized. Cycle. Unless you have well, so that's hidden in the definition of EG and BG. So in the definition of EG, there are various G1, G2, G3, ... right? So I didn't explain to you that, yeah, I think I didn't answer correctly to Okada-kun. I mean, so there are simplices labeled in different orders by the same element, for example, right? And in EG, I think these two simplices shouldn't be two separate simplices, but one simplex with a different name assigned. Shouldn't be the case, sorry. No, that shouldn't be the case. So your question was, where did we use the No, I don't think you actually use it. Yeah. Sorry, I need to relearn the basics again. let me answer you next week or yeah. I think you can define the map from each simplices to BG one by one. But in order to show that the resulting maps from each simplices to the simplices here, to patch up correctly, to define a continuous map from this to that, you actually need to have that they satisfy the co-cycle condition. Otherwise they don't correctly patch up. Yeah. So,
What's that? So it's like Gij times JK times JKI.
yeah. So
But I thought you've already used it because you like I mean. The part you can represent that triangle using only like two group elements. It isn't. It's not already using it. The fact that the group multiplies to an identity.
well, if we have a look only at this simplex labeled by three group elements, we can always decide that even though this might not satisfy this, I mean, in any case, we need to give an order to the vertices of a given simplex. And we can just always declare that a triangle labeled by Gij on the 0, 1 edge and Gjk labeled on 1, 2 edge to be mapped to the simplex of BG labeled by two elements Gij and Gjk. That's perfectly doable, right? That's perfectly doable. So if we have a arbitrary two-dimensional simplex complex labeled by Gij, which does not satisfy co-cycle condition, we can randomly say that each of the simplex is mapped to the two simplices on this side, labeled by the two of the edges, given preferably chosen by the given ordering of the vertex. You can write a map.
Oh, I see.
Write such a map, right?
You can still write a map.
Yeah, you can write a map, but it is not guaranteed that such a map defines a continuous map from this to that, because there are not just this triangle, but there are other triangles which needs to patch up correctly to form a continuous map. Yeah. It is. Yeah, I said something wrong trying to answer your question, saying that these two are actually the same cell. It is not true. In this particular construction of BG, I'm introducing tons of redundantly looking cells labeled by a permutation of a single chosen subset of G, but that's actually necessary in the discussion which follows. I should say that though, that as a space, BG is only defined up to homotopy so the construction I gave was a particularly nice explicit one, which is one example of BG, but there can be many other BGs, which is as a space different, which has different choices of simplexes, etc. So for example, you can require that no two consecutive group elements, labeling them, are equal, for example. So we can try to remove obvious self loop. That's doable. It is known you can do that and remove some of the cells. Or another common construction of BG is the following for the finite group. So suppose you already learned how to construct UN, sorry, BUN, right? Then you have a bundle, UN bundle over BUN. Of this form, right? Then this space is contractible. And then UN action is free. Right? So let's say G is a different finite group. Right? And the G acting on Cn is a faithful representation. By faithful, I mean only the identity element fixes Cn. So this means so this realizes G as a subgroup of UN. Therefore, this G also acts on EUN in a free fashion. This means that for sufficiently big UN, such that it contains G, EUN satisfies both the conditions necessary for being BG, sorry, EG. So EUN is also an EG space. So in this way, you can construct BG for the finite group to be just EUN divided by not by UN, but by G. So BG constructed in this way is as a manifold. I mean, this is a nice infinite dimensional manifold because although I haven't told you, I mean, BUN, EUN are nice infinite dimensional manifolds. It's smooth. You can do differential geometry on it. And and this is a infinite dimensional smooth manifold divided by a finite group. So BG is an extremely nice space if you construct it in this manner.
Wait, so BG is smaller than UN, is that right?
I have zero idea how to define smallness or largeness in the infinite dimensional context.
Sure, but you're dividing it by all of.
Yeah, BG is bigger than BUN in that sense. So you shouldn't try to assign bigness or relative size for infinite dimensional manifolds. I mean, because you can take identity, right? As a subgroup of UN. This means that B identity is not even BUN, but EUN itself. It's a contractible space. But homotopically, contractible infinite dimensional space is just a point. I mean, E,
You're also taking multiple equivalents. I'm confused about it now.
as a, what,
Oh, I see, I see. Right.
I mean, you need to pick a particular space, but the final result only depends on the homotopy class BG. But you need to pick a particular one to talk about a map from a space to the other space. You cannot first define the homotopy equivalence class and discuss a map from another manifold. Yeah. So this is a nicer. This is nice and smooth. So in some sense, this is better for some type of computations. And the combinatorial descriptions I gave you during the first hour of my lecture today was much more singular, but is useful in some other respect.
Sorry, let me correct.
Yes.
These two construction and BG,
Yeah.
these two BG are super different.
Super different, right?
But it is homotopically.
That's right, because it's guaranteed by the general proposition we discussed last semester. Both are infinite dimensional, yeah. But one is very smooth, the other was very complicated. But this complicated one only has very explicit cells, which can be named directly. So if you want to do some kind of combinatorial computations on computers, that's definitely better. So if you are curious, let me just remind you why there are, if you have two classifying spaces, they are homotopically the same. So suppose we have one classifying space, G, EG, BG, and another classifying space, let's temporarily call it E prime G and B prime G, right? So for both BG, this property is satisfied. I erased, but G bundle on any space is specified. So let's consider this B prime G as the classifying space, and this is the random space you are considering the G bundle on. Then because this is a classifying space, you have a map from this to that. And this G bundle is obtained by pulling back this G bundle using this map F1, right? So if you think of this as M, any G bundle should be obtained by having a map from M to BG and pulling this back from here. Conversely, if you reverse the role of the two, you have map in the other direction, because you can think of this as the space you are considering the bundles on, and this as the classifying space. Then you have a map F2 from this to there, such that the bundle G bundle here is a pullback of this to that, right? And because this G bundle is a pullback of this G bundle, and this G bundle is a pullback of this G bundle, if you combine the two, this G bundle, I mean, we again use this general principle that the G bundle on a space is equivalent to homotopy classes of maps. By composing these two maps, you can see that G bundle, I mean, this G bundle pulled back by this composition is equivalent to itself. Using the universal property, this means that the composition of F2 and F1 is homotopic to the identity by the universal property. You apply that to on this side too. Now we have shown that F2, F1 is homotopic to the identity, and F1, F2 is also homotopic to the identity. This established the homotopy equivalence of BG and BG prime. So by the universal property, anything which classifies G bundles are homotopically equivalent. So BG constructed this way, and BG constructed combinatorially during the first 1 hour of the lecture needs to be homotopically equivalent. Therefore, the cohomology defined on BG should be equivalent on both sides, but the actual computation of cohomology group can only be done effectively in one of the definition, and that's what I'm going to discuss now. So let's come back to this point. So let's discuss HK of BG A. So A is an abelian group. And this is the space we just constructed. To discuss this, we need to study the space of K-chains, which is CK, BG, A, sorry, K cochains. So recall that K cycles are something like this, right? So K cochains are an assignment of a value in A for each cells of this form. So it's just a map from G to the power K to A. So let's write such a function just as G1, G2, comma, Gk. But I could also use just as a notation bars to denote such functions. But I don't see bars used in the descriptions of the cochains very often. So let me just use commas. Maybe using bars might be more appropriate, but this is K cochain. Then delta F should be a K plus 1 cochain, right? So G1, G2, Gk plus 1. And this can be determined from the space map I discussed about 20 minutes ago or something. And that's given by F, G2, G3, Gk plus 1, minus F, G1, G2, G3, G4, Gk plus 1. And plus F, G1, G2, G3, G4, Gk plus 1, minus F, G1, G2, G3, G4, Gk plus 1, and then plus minus 1 to the case F, G1, G2, Gk minus 1, Gk plus 1. I hope the sign is right. And then you finally have minus 1 to K plus 1, F, G1, G2, Gk. So this is delta, reactions of delta. This follows from the explicit construction of BG and the way the cells of BGs are patched up. So you can show that delta squared F is 0. And HK of BGA is kernel of delta over image of delta. So that's the definition of the group homology. But that formula is very, very complicated. So let's look at them one by one. So let's talk about H1. Right? So we need to understand one cochain. One cochain is something like this. So it's a map from G to A, right? And then you'd like to impose the condition that delta F is 0. What's delta F? Delta F is a two cochain. So it has two arguments, GH. Following this general formula, you just have F of H from the first term, and from the second term, you have FGH, and the third term is this last one, plus FG, right? So this just means that, so delta F equals 0 means that FG plus FH is equal to FGH. This means that FG to A is a homomorphism. So we learned that H1 BG A is just the set of homomorphisms. I didn't discuss image of delta, but image of delta becomes 0 in this case. So you don't have to quotient anything. This is it. So today I'm just going to discuss H2 and some of its manifestation. That will be about it, but let's continue. So now the next step to discuss is this. Before going further, I should say that the computation of H1 of BG of A, if we use the other definition of BG, dividing EUN by G, won't go as simple as that, because EUN has a different nice features, but not as useful as this. So it will be a totally different computation, but homotopy equivalence guarantees that that totally different computation eventually gives us back this result. So that's the strange thing about algebraic topology, but that's it. I forgot to say another comment. So I introduced these cohomology groups as the ordinary cohomology group of this classifying space of BG, but the algebraic formula I just erased in terms of cochains defined as a map from G to the K to A, with delta defined with that particular formula, can be motivated from a totally different perspective, just from algebraic consideration on functions on G. And from that perspective, this same object is usually called group cohomology. And in that area of mathematics, this is often just written as HK of G of A without putting the letter B, which is very, very confusing, because in physics, we often need to discuss HK of UN as when UN is a space, and in this case, this is definitely different from HK of BUN of A. So we just don't use this notation of HK of B semicolon G A to denote group cohomology, but you should be aware that there are physics papers which also uses the other notation. So it's just a point to be aware. Another comment is that in this kind of cohomology and other algebraic topology analysis, we often have two separate definitions. One is basically very algebraic, another using more geometric objects. So here we have an algebraic definition of group cohomology, and we had a space definition of group cohomology. And there's a general principle in algebraic topology saying that any algebraically defined concept can be represented as a homotopy equivalence class of maps from the space, from some classifying space. And that can be used in an effective way in various cases. And this is a first instance of such principle. So that's what's going on. So, but let's come back to this H2. Go ahead. Yes.
Is there any, in general, I believe that the HKGA and HKBGA is they are in general different. But is there any constant to their
It is never the same. I mean,
that's one. Yeah. That's the problem of the notation. Right?
yeah, it's just a problem of notation. Yeah. So I really hope people just stop using this confusing notation of dropping B. But yeah.
In the context of group homology, always there's B, so sometimes.
Yeah, right.
Some guy dropped the bomb.
That's right. That's right. Yeah, it's unfortunate, but so for H2, F is a two cochain is a function of two variables, right? And delta F is a function of three variables, and if you use the general formula, this is FHK minus F GHK plus F GHK minus F GH. So demanding that this is 0 means that FHK plus FGHK is equal to FGHK plus FGH. So this is a weird condition. But you have encountered this before, first in the elementary school, but then in the quantum mechanics class. So let me explain why that's the case. So let's discuss a central extension of a group. So this is the exact sequence of groups. So let's remind ourselves what's the meaning of this sequence. So exact sequence is such that there are homomorphisms, and you always have the image is the kernel. So this just means that the map from A to gamma is surjective. And injective. And gamma to G is surjective. This means that A is effectively a subgroup of gamma, and G is its quotient. So this means that G is gamma over A. And the general theory is also interesting, but let's, for simplicity, assume assume A is central in gamma. And central in gamma just means that if you pick random gamma and random A, then A gamma is gamma A. So A commutes with everything. So in this case, because this is injective and this is surjective, for each G in G, so we pick an element from the quotient. We pick an element in gamma such that gamma G is mapped to G, right? Pick an element A, then you can multiply A and gamma G, and this gives A gamma G gives an element in gamma. Every such element is distinct for distinct choices of A and G. So as a set, this is equal to A times G, but the group multiplication law can be different. So what happens is that consider multiplying gamma G and gamma H. Gamma G and gamma H is in gamma. So you can send it to G. And because we assume that this is a homomorphism, this is sent to GH. And GH is this. GH also comes from gamma GH. So the difference, I mean, if you take the quotient, they are mapped to identity. And because of the kernel equals image condition, it's necessarily an element of A. So this means that gamma G, gamma H from this, you see that gamma G, gamma H is equal to A GH of gamma GH for some choice of A. Let's study what's the condition we have for this AG of H. So for this purpose, let's consider the triple product, gamma G, gamma H, gamma K. So first, we can combine the first two elements, giving rise to AGH, gamma K. And this is AGH, AGHK, gamma GHK. So this is one way of computation. But you can first combine H and K. This gives you AHK, gamma G, gamma HK, which is AHK, AGHK, gamma GHK. So because of that, in order for the multiplication rule of gamma, capital gamma to be consistent, this product needs to be equal to this. So we need to have AGH, AGHK equals AHK, AG, comma HK. So you see that this relation is just this relation written in the multiplicative notation. So H2 of BGA somehow is related to this group extension problem. But so far, I only explained that group extension problem is related to delta A equals 0 condition, right? So this only explains H2 being a kernel delta part, but you need to divide by image delta part, right? So how will this condition emerge? That comes from this part. I said that for each G, I pick gamma G. But you can also take a different gamma G, which I denote as twiddle gamma G, which is, say, gamma G times element, say B of G, which is in A. In this case, we can compute gamma twiddle G, gamma twiddle H, which is BG, BH, gamma GH. And we need to convert this back to gamma GH twiddle. Sorry. I need AGH, gamma GH. And we need to relate this to, again, so BG, BH divided by BGH, AGH, right? So this means that this piece is the twiddle GH. And the factor here we are seeing is exactly delta B GH in a multiplicative notation. So this quotient by image of delta is related to the random choice, different random choice of the elements gamma G appearing in the construction. So this establishes the condition that, I mean, the statement that elements of BGA classifies equivalence classes of this extension, a central extension gamma G. So this is kind of intriguing, right? We introduced BG as a space which classifies G bundles. And we applied the machinery of the cohomology groups we introduced in the last semester to that space. And we got something very algebraic. And we computed it explicitly for H1. It turned out to be just homomorphisms. And for H2, it classifies this central extension. I'd like to discuss two examples today before closing. One is what you learn in elementary school. Arithmetic. So as an explicit example, I consider this. Extension of Z10 by Z10, which is Z100. So this map is given by multiplication by 10. And this map is given by modulo 10. So let's denote this element A, B, and this element A. And denote this element by A comma B. Right? so for element 1, I write this. Element 9, I write this. And so this was gamma 1 in my notation in the previous 5 minutes or something, right? Gamma 9. But the product, and I'm using an additive notation, so gamma 1 plus gamma 9 is gamma 0 because it's modulo 10, but you have some element here, which is 10 times A19. You see? This means that this extension is associated to the cocycle factor. Oh, I shouldn't have used A and B. Yeah, or let's say omega A1, A2 is 0 when A1 plus A2 is less than 10, and 1 when A1 plus A2 is larger than 2, so larger than 10. So this is what we learn in Japanese elementary school as kuriagari. And which is in English called carry. If you learn basic computer science, there's an operation called carry in the CPU. So you have actually encountered the group extension and the concept of second cohomology or the cocycle condition in your elementary school when you are 6 or 7. Have you ever checked that your Kuriagari computation satisfies the two cocycle condition? The delta of omega is 0. But you should think twice why it was okay for not actually checking the cocycle condition to do all these computations in your elementary school. Because otherwise, your computation would become inconsistent, right? So somehow, instinctively or in some other fashion, we should have internalized at that point the concept of the consistency condition coming from this cocycle condition. So I don't remember exactly where I read this first, but there's a very nice article by a mathematician, Isaacson, on this point. And this Isaacson is the person who is the very, very expert on the computation of the homotopy group of spheres I introduced in the last semester. So this fascinates mathematicians too. Another example is the projective representation in quantum mechanics. So let's say H is the Hilbert space of some quantum mechanical system. And you have an action of a symmetry group. Symmetry group G. Usually, such an action rho give you rho of G as a unitary matrix acting on the Hilbert space. Let's use UG instead. And the most obvious condition we use is that UG, UH is equal to UGH. In that case, you get the representation of G. However, we know that a ket in Hilbert space and complex number times a ket, where C is a complex number with absolute value 1, so it's in U1, which we regard as the set of complex numbers with absolute values 1. These two vectors in the Hilbert spaces are the same, physically, right? I mean, there are people in quantum mechanics community who don't like ket anymore, and people these people use density matrices all the time. So C shouldn't be there from the start. So you can relax the condition that U and G, UG and UH compose to UGH, but there's a map, sorry, there's a phase C of G comma H, which is in U1. So you can weaken the condition. So this is the projective phase. In such a case, this is known as a projective representation. And in order to make a contrast, sometimes you say that this is a genuine representation of G. So in this case, these operations do still compose correctly if you consider them as acting on the density matrices, but not on the vector vectors themselves. And in such a case, I mean, this is exactly the same condition we had before, right? So C of G comma H is a 2 cocycle. And determine an element of H2 of B, G, comma, U1. Again, this is a kernel delta over image delta condition, right? And the image delta part corresponds to the different choice of UG, which is related to the original choice of UG by some phase depending on group element B of G. So if you take the position that the phase of a ket vector isn't important, you are perfectly free to redefine your unitary operator by multiplying by a phase, and that gives you the degrees of freedom you have in this image delta part. So this is the end of today's lecture. Next week, I discuss this example from the point of view of the easiest example, simplest example. Of quantum anomaly. And how this arises at the boundary of 1+1 dimensional symmetry protected topological phases. So that's the thing we are going to discuss next week. So thank you very much for your attention today. And you can ask more questions if you like, but this is the end of the lecture today. Thank you. Any questions?
I know this is slightly ahead of the topic, but
That's fine.
You're going to use like higher cohomology. We want to consider like
That's right.
SPT.
That's right.
I'm wondering. So there's anomaly in 2D CFG.
Right.
Trace anomaly.
Yeah. Trace anomaly.
Is it also this?
I don't think so. This type of anomaly nicely visible in algebraic topologies are all parity odd anomalies, which appears as a complex phase in the Euclidean weak rotated versions of theory.
Don't you say that the Virasoro algebra is the central extension of the algebra?
Virasoro is a bit different. Yeah.
Why is that?
That's a good question.
You're saying that a trace anomaly wouldn't be represented like this, right? That's what you're saying. When you say that.
That's right. That's right. In 2D CFT, if you have an affine algebra, I mean G-level K symmetry, then that K can be definitely treated in this manner.
I see.
Yeah. I don't understand. Yeah, I don't know why it applies to the Virasoro case. Probably because it's in the case of 2D CFT, you have two central CL and CR, right? And CL minus CR are the parity odd part. And this part is definitely visible in this approach. Yeah. Yeah, but CL plus CR part, the more ordinary part of the central charge, I don't think it appears
I see.
in a very nice way in this algebraic topology approach.
I think textbooks have been like lying to us about it. Some people say, Virasoro is an extension of where.
No, I mean, mathematically, there's nothing wrong
Fine.
in saying that Virasoro is a central extension of the diffeomorphism group.
At least they're only talking about holomorphic parts, so they're only.
Yeah.
CL, so
Right.
That makes sense. Okay. CL minus 0,
Yeah, I mean, if you put one side to be 0, then that's doable. But yeah, that's really tricky. I mean, the modern algebraic topology approach to anomalies is very precise in the sense that it not only tells us the general structure of the infinitesimal part of the anomaly, but also the quantization. So if you apply this type of algebraic topology approach to the chiral central charge, it predicts the quantization that it's quantized to a half integer in the spin case and to 8n in the non-spin case. So that comes out of algebraic topology. But we know that CL plus CR is not quantized at all, right? So that non-quantization of the CL plus CR doesn't come out as naturally from this general approach.
But there's a way to. Is there a way to like study continuous anomaly using that?
If you just want to have a understanding of the continuous anomaly,
Not even about like any continuous anomaly.
then you can just use the well-established anomaly polynomials from decades ago, and you don't get anything new. So yeah, that's a tricky part. No problem. So thank you. Yeah, that's a good question.
It's slightly ahead of it.
In fact, it's very ahead of the point because I'm not going to discuss any anomalies related to the real part of the Euclidean partition function. Yeah, this approach only gives us the imaginary part of the Euclidean Wick-rotated action. Other questions? I mean, it's really the end of the lecture, so you can leave. We would infinitely continue. So let me stop the recording.